This is your second lesson on reflection. Last time you have done the Snell's law experiment and you have learned how to do calculations using the Snell's law. And this time you will see different applications of reflection. There are 4 different sections in this lesson. Number 1, image formation due to reflection. Number 2, the calculation of speed of light in different medium. Number 3, the reflection by rectangular block and prism. And lastly, number 4, dispersion of light. So here we go. We start from page 35. Due to reflection, there is image formation. Before we talk about image formation, let's see what happens to light when it travels from air to glass. You will see that it bends towards normal. What I mean is, the angle in glass is smaller. When we have air and glass, and light ray travels from air to glass, you will see when you draw a normal, then the reflected angle in glass is smaller. We say the light ray bends towards normal. And this can be important if we want to explain the following picture. The picture looks funny because the body of this man moves to the right. But why? Let's draw a ray diagram and explain what happened. Now we draw a ray diagram of this level, that is W, X, Y, Z. And you can see this light ray that comes from his body, which refracts and bends away from normal. And then we can see there is a virtual rays that points backward. Similarly, we may draw another light ray which also bends away from normal, and then we produce it backward to find the image position. You can see that the image is on the right, and that's why the body of this man moves to the right, because his body is under water. And let's do it again. In top view, light travels in water and bends away when it goes into air. Produce the reflected ray backwards. Do it again. Produce the reflected ray backward. So you may locate the image which is on the right. There are many similar examples such as these. A fish in water or a corn at the bottom of water. So for the situation like this, when the observer observes the fish underwater, we may draw a diagram which is a side view. We draw light rays from the object that goes into air but bend away from normal. We draw another light rays, it also bend away from the normal. We produce the reflected rays backward. In this way, then you may mark the position of the image, and you can see the image is a little bit higher in position than the object. And you should note that where you see the fish is not actually there. And the other example is a corn at the bottom of a cup. Let's draw a ray diagram to illustrate the idea. We have a cup, we have a corn at the bottom. There's an observer, but at that time the observer just cannot see the corn. What we do is add water. When we add water, then the light ray will go this way. It bends away from normal so that the light rays go into the observer eye. And that means the observer can see the corn now. The another example is a stick that partially dipped in water. It appears bent. Why? You can see the ray diagram at the bottom of the page, and this ray diagram is almost the same as the one on the last page. What you have to do is to draw 2 light rays from the end of the object, and these light rays bend away from normal when they are reflected on the water surface. In this way, you may draw virtual rays to find the image. So after you have found the image of the red dot, which we mark it blue, then you may draw the image of the whole part underwater in this way. In nature, An archerfish produces a water jet to hit the bugs above water. However, if the archerfish finds a bug at that position, due to the refraction of light, the image of the bug will appear here, so the fish will miss the target. On the other hand, if a fish target and a bug directly above it, there will be no reflection of light, so there is no change in direction. Similarly, a great blue heron also have the same problem, and that's why it usually targets at its dinner by looking normally to the waters. And now let's move on to the second part, refraction and the speed of light. The refractive index is indeed a ratio of the speed of light in vacuum and the speed of light in that medium. Simply speaking, when the refractive index is higher, when this number is larger, then the light speed in that medium would be lower. Well, how to use that formula? Let me show you how to find the speed of light in water. We have the refractive index of water to be 1.333, and that equals the speed of light in vacuum, which is 3 times 10 to the power 8, over the speed of light in water, which is V here. And using your calculator, you can easily find it to be 2.25 times 10 to the power 8 meter per second. Now, part 3. Refraction by rectangular block in prism. First of all, rectangular block. When light ray travels from air into rectangular glass block and then out into air again, there are 2 refractions. Let's do some simple calculation, such as this. For the first refraction, the glass block has a refractive index of 1.6 here, and it has an angle of incidence of 35 degrees. So we may do the calculation like this, which is 1.6, that equals psi I over psi r. I, in this case, is 35 degrees, and r that we are going to find. After that, then we may do the second refraction on the other side. We may know that the angle r from the first calculation using Snell's law, so you should have a value here from your calculator. We now do the second refraction. In this way, also 1.6 that equals psi I over psi r. Yes, it's the same, psi I over psi r. I is the angle in air, and r is the angle in glass. And of course, you will find the angle I in this way to be 35 degrees again. So this calculation just want to tell you that the incident ray and finally the emergent ray, they will be parallel to each other. And if they are parallel, but the light ray moves sideways, then we say the light ray has a lateral displacement. That means it moves to one side. On the other hand, for a prism, the light ray bends towards the base. It will turn closer to the base. Compared with the original direction, the light ray is deflected, and this is called the angle of deflection. You may notice that white light is separated into rainbow colors when it passes through a prism. This is called dispersion of light. The reason of this is because different colors travels at different speeds in glass. That means they have different refractive index. Indeed, they refracted differently. You can see that red light deflect less and violet light deflect more. So the refractive index of violet is larger. It travels slower.